Hey, good afternoon, colleagues, students. Today we are happy to have Professor Lee from Zhejiang University. Actually, we have two guests. Another Professor He, he is going to present a talk tomorrow on MRI. And today we have Professor Lee. He is going to talk about macromolecular dynamic. Let me give a brief introduction of Professor Li. Professor Li Jingyuan, he got his bachelor degree and PhD degree both in physics from Zhejiang University, and then he went to Columbia University to do postdoc research, and after that he returned to the Institute of High Energy Physics at the Academy of Science, Chinese Academy of Science, as a professor in the multidisciplinary research division in 2011. And then a few years later, 2017, he came back to Zhejiang University at the Department of Physics as a professor. Professor Li, he was selected as this 100 Talents program of Academy of Science of Academy of Science, Chinese Academy of Science, 百人计划, right? And then he was also found from the National Science Foundation, this excellent young science fund, 优秀青年基金. So his research is mainly focused on computational life matter physics, and especially on intrinsically disordered protein, on the characterization, understanding, and predicting the conformation or interaction. So this is especially relevant because we have two new assistant professor, Dr. Zheng, Dr. Tang, are working on protein and dynamic, and especially Dr. Zheng is also working on this intrinsic disorder protein, but more like in a system related to like phase separation, right? Yeah, let's welcome Professor Li.
Okay, thank you all. So it's really a pleasure to be here and present our studies, and I want to thank Cheng Song for your invitation and arrange everything. So basically, we are doing computational studies of biological macromolecules. So we are focused on, since we in the School of Physics, so we focus on trying to find some correlations within these seemingly random or irregular biological macromolecules. So as we all know, there are various structural components within these so-called macromolecules. Like, so we have residues within proteins, and we have bases within DNA or RNAs. And apparently these structural components have various multiple interactions, like hydrogen bonds between bases, hydrogen bonds between backbone residues, and electrostatic interactions, and cation pi interactions, and so on. So we all know these interactions between these structural components are correlated in various ways. So, for example, the protein folding is often regarded as a first-order transition. So it's a kind of on-off transition. And the structural stabilities of these macromolecules are largely attributed to these correlations. And apparently their biological functions, their structural dynamics is also related to these correlations. So, and compared to the proteins, the DNA or RNA largely attend so-called linear structures. In that way, the correlations or couplings between these interactions between bases are much weaker as compared to the proteins. so they can, correlated coupled together. So in many cases, people think the DNA or RNA do not have a structural rigidity. They largely have structural flexibilities. And as I will show you later, it's not apparently true. So the most apparent way to show the coupling or correlations between these residue interactions is this case. So as we can see, this, between parallel or anti-parallel beta sheet, there are multiple backbone hydrogen bonds. When the proteins sustain under the mechanical force, and these coupled backbone hydrogen bonds can resist the mechanical force in a cooperative way. And that results in a highly mechanical stabilities of protein. So that is basically the way we understand or we learn for the proteins. And so-called protein is mostly a structural protein, the protein with finite structures and DNA RNAs. While as we are getting aware that there are large varieties of proteins that do not have well-defined structures, and we can call them intrinsically disordered protein, or they have pretty extended intrinsic disorder region (IDR). And as we getting know, this IDP or IDR play an essential role in various biological functions. So the apparent questions we can have is whether within this seemingly random or highly dynamic IDP or IDR, there are still some correlation between these residue or residue interactions. And as I will show you later, there are we can still find some cases with considerable correlations between residue interaction. So the first cases I will show you is a muscle adhesive protein. So, as we can see, that is muscle, and they can secrete muscle adhesive proteins to absorb the minerals. And so that kind of protein, their functions is to realize underwater adhesion. In that way, they can effectively adhere a wide spectrum of these hydrophilic materials in salt solutions. Since the muscle, they should not choose a specific mineral to the salt. And that kind of protein is also IDP. As we know, the protein absorptions on some given substrate, they need to overcome a considerable barrier result from this stable hydration on these hydrophilic materials, and they're so-called dehydration barriers. As our daily life, we need to wash our hands. That means we use water or hydration to remove the absorptions from protein. So that's basically the way we do. So, so the muscle adhesive protein, has a superior underwater adhesion ability. So apparently they can attain intense interest. So in previous studies, they found or they think this adhesion ability can be related to two kinds of residues. One is dopant. A DOPA is a post-translational modification of tyrosine, and the other is lysine. So basically, we just do large-scale MD simulations to sample the conformation in sample or conformation space of muscle adhesive proteins. So we can find there's a very interesting structure feature is that the DOPA can exhibit considerable spatial correlations with this positively charged residue, lysine or arginine, and they can form essential residue pairs. So basically, we can do the whole scaled contact matrix with respect to the residue type, and we can see the correlation between lysine and DOPA and arginine with DOPA is much higher than the other residue combinations. So it's a very statistically considerable things. So then we try to understand why they can have such considerable correlation. It's attributed to the relatively modest interactions. It's kind of cation pi interactions. And since these two residues have similar size, so they can have an essential hydrophobic matching effect. So, but this kind of residue interaction is quite modest. But we have another advantage, is that the lysine and DOPA has most abundance residues. So that cause the formation of these residue pairs is quite ubiquitous. So we can always find 1, 2, 3 residue pairs within these seemingly random or irregular protein structures. An average number is kind of 2.7, and it's pretty enough for this kind of residue pair to realize the protein absorptions, as I will show you later. And we can also use autocorrelation functions to test the lifetime of this residue pair. It's kind of 200 picoseconds, and that is also quite important features. And later we use this structure, protein structure, to test their absorption processes on these super hydrophilic materials called mica. And we can see the protein can quickly absorb on this surface. And we can find the whole absorption process is kind of step-like. And for each step, 1 or 2 residue pairs dominate the protein absorption. So it's quite essential law for protein absorptions. And the picture is this. We can see, since there's a stable hydration layers on top of this mica, so both residues are swinging on top of this hydration layer. And as the swinging of DOPA, he can temporarily drag the water molecules from this surface and locally reduce the stability of hydration layer. So if there's no another residues nearby, the water can diffuse from the other way to fit this hole. But since there's another residue like lysine or arginine, it can fit the hole and directly interact with mica and realize the absorptions. So it's kind of cooperative way to realize absorption. And so basically, there are two kinds of action mode: the screening of DOPA and the digging of lysine. So we can, so that's under the suggestions of Changsong. We use this close correlation function to test the interval of these two actions. And as we can see, the time delay of these two correlated motion is like 34 picoseconds. And it's much shorter than the lifetime of residual pair. So in that way, even though the residual pair is quite dynamic, and its temporary formation of this residual pair is stable enough to realize the protein absorption. So in this stage, we tend to realize it seems has nothing to do with DOPA. It's just aromatic residue should be enough. So it has nothing to do with post-translational modifications. So we try to, since we are doing computation, and basically we can do whatever we want. So we can just remove the modification, the additional hydroxyl group, and just do the pure tyrosine. And we can see the same thing. We can still find the similar spatial correlations between lysine, arginine, and tyrosine. And they can still realize the similar absorptions. So we tend to believe two things. The first thing, the absorption stability or absorption ability of muscle adhesive proteins is just the residual pair. It has nothing to do with tyrosine post-translational modification. And the other is there's spatial correlations between these two kinds of residues. So we use NMR to test the spatial correlations between tyrosine and positive charge residues. And we can have this spatial signal to for these correlations. And under the help of Cao Yi's group from Nanjing University, we test the absorption stabilities of muscle adhesive proteins and without post-translational modification. And they can realize a similar absorption stabilities. So it's a pretty good test. So that is first case I want to show you. And the other case is the IDP's interactions. And as we can see, at this stage, the IDP interactions is often related to the liquid-liquid phase separations. In other words, there's in space, they can separate from a low density concentration to form a high density droplet. And then and the IDP interactions is considerable as a driving force for this formation of this high density droplet or liquid-liquid phase separations. And as we often think is that the IDP is highly dynamic, and the conformation is highly dynamic, and the interaction is also highly dynamic. So we are wondering how IDP can realize or form stable interactions. And the other way is, these reversible interactions, how these reversible interactions can be correlated to this conformation frustration. So that is two things we want to test or we want to study. So, since we just, everyone is in the initial stage to study the IDP interactions and IDP conformation fluctuation. So we just do very basic way to test these two processes, the conformation fluctuations and the reversible interactions. So firstly, we just use this very basic parameter to describe the IDP conformation, radius gyrations, which means if a protein is extended, the radius gyration is large, and the protein is compact or in the global-like, and the radius gyration is small. And we can just, it's a very simple way to describe the protein structures. And we can find this histogram can be fitted into two Gaussian distributions, which means the protein ensemble can largely divided into two subspace, the compact conformations and the stretch conformations. And the conformation fluctuation can roughly be described as the switching between these two domains. But as I say, it is just very rough and very basic way to do these things, since we are in the early stage of IDP. And we just do this large scale, unbiased MD. Since we try to take some enhanced sampling, but what enhanced sampling can really accurately describe the interaction dynamics. So we just do this unbiased MD, and we collect like 60 events of this reversible association. And we can find this survival probability can largely described as these two double exponent decay. That suggests us they may be roughly divided the association event into two kind of domains. The transient compact and stable associations. And we can just using this fitting parameter to have this threshold value to divide two classes of association event. So we can roughly divide the conformation ensemble and association event into two classes. So that is association event, and that is conformation ensemble. And we can find very unique correlation is that if we have very compact residue or IDP, we cannot realize stable association. In other words, the stretch conformation is a necessary condition of this stable association. We can have a stretch conformation and has this transient association, but for all sustained associations, we just have sustained stretch conformation. And the idea is that there's a finite region. We can find there's a finite region in the certain C-terminal part of IDP. They have much higher property to mediate this stable association. So the stretched conformation can facilitate the exposure of this hard region and realize the subsequent involvement of this region. So in other words, on the other hand, the compact structure, this hard region may be embedded or buried inside the IDP, and they can impose the spatial restrictions on the involvement of this hard region. And still, it's all about the MD simulations, and we need some experimental verifications And it's also from the help of Cao Yi's group. And we test this. We just test only one thing: is we cut the C-terminal part and N-terminal part, and to see their liquid-liquid phase separation ability compared to the Y type. And we can see, if we cut C-terminal part, the liquid phase separation is suppressed. And if we cut N-terminal part, it's largely the same as Y-type proteins. So that is briefly validate our simulation result. So that is the two things about the proteins, especially the IDP. And as I just in the discussion, in the introductions, I mentioned, compared to the proteins, the DNA or RNA, they largely adopt a linear configuration, and there are correlations between these base hydrogen bonds are limited, and that results in very weak mechanical stability. Well, in biological world, there's always exception, and that is exception. In the case of assembly of virus, so as we can see, the virus largely, has two parts: the protein capsid and the DNA or RNA within this capsid, and that they require a motor called DNA packing motor to pack the DNA into this capsid. So we can see this within this capsid, the DNA is very condensed, and there's a very high DNA confinement, and the pressure estimated value is around 50 atmosphere. And it's a very famous picture. Is once the capsid break, the DNA or RNA can expose a pretty large region compared to its capsid. The DNA packing motor is considered as one of the strongest motor we can have, and its workload is up to 57 piconewton. It's huge workload, and its star force is even higher than the myosins and kinesins, like 8 tons. Myosins and kinesins like this, and drag a huge vesicle. And DNA packing motor is much higher workload compared to the myosin or kinesin. So that is one kind of DNA packing motor. It's composed of 3 parts. A connector is imposed to the entrance of capsid. ATPase is a motor to push DNA into the capsid, and the connector and in between is 7 pRNA, and pRNA is kind of the motor's hinge to connect two parts. So as we can see, or as we can understand, this pRNA bear considerable portion of mechanical force, right? It's huge workload. So that means this kind of RNA should have huge mechanical stability. This kind of RNA is called 3-way junctions. So that means there are multiple DNA strands. They can intertwine together to form these junction structures, like holiday junctions, 3-way junctions, and so on. And since they can have multiple handles, so they can hold the different component of motor of this biomolecular machines. So in this case, the DNA packaging motor, we have this three-way junction pRNA. So it has three handles or three helix. So the helix 1 connect to the ATPase, the driving machine, and the helix 3 connect to the connector, this one, and the helix 2, is linked to the other pRNA. So as we can see, the H1 and H3 in these directions can sustain a huge workload, during the packing of DNA strand. So, we just do simulations, and we just see these things. Okay, we have a huge rupture force to peeling the DNA, the pRNAs in this H1 and H3 directions, huge one. And we notice this, it's actually, this mechanical stability is not from the hydrogen bonds between these bases. This actually results from the two magnesium ions, we in this hinge. So if we remove these magnesium ions, we can just, this mechanical resistance just disappear. And this mechanical force is very huge. It's like 2,000 piconewton. It's comparable to the most mechanical resistant proteins like GB1. So if we can see this magnesium clump in details. We can see this, these two magnesium ions is located very close to each other, and they can forming two neighboring magnesium clump. And the mechanical force need to rupture these two magnesium clump simultaneously. We can see these separations between these two bases simultaneously, so they can reduce the mechanical force in a cooperative fashion. And that breakage of magnesium clump trigger the unfolding of whole pRNA. Again, it's quite weird, quite bizarre, for the people to understand there's a huge rigid RNA. So we need some experimental verifications. And again, we also have for Cao Yi, and they do this kind of atomistic force microscopy. This single molecular technique to test the rupture force of this three-way junction pRNA. And as you can see, they did, realize a huge mechanical force. It's like 220 piconewton. Since the rupture, the pooling velocity of simulation is much faster than the experiment, so it's kind of one order of magnitude smaller in the experiment, but it's still higher than many other in the same pooling velocity. It's still higher than many other mechanical proteins. So it did realize a huge mechanical force and stability. And such stability is largely attributed to the magnesium ions. If we have some chemical way to remove these magnesium ions, and the rupture force reduced to something like 70 piconewtons, and it's much smaller than the original one. and we can also build a phenomenological model to test the lifetime of pRNA under the workload of this DNA packaging motor, like this one. And the lifetime is like 26 seconds, and it's pretty enough for the pRNA to realize the whole things, the whole DNA packing things. So that is the way we can understand, or we learn that the DNA or RNA can still realize a very stable stability of mechanical stability with the help of magnesium ions. Since the ions, is intensively interact with proteins or these biological macromolecules. And that's another cases called cation chloride co-transporter, KCC. This cation is a potassium, so it's a potassium chloride co-transporter. In that sense, this transporter can transport a pair of ion pair together. So we start from the cryo-EM structures from our collaborator. We can identify 3 ion binding sites. So there are several questions we want to answer from our simulation. The first one is whether this KCC can realize the coupled transportations of this ion pair. So we need to estimate the correlation coefficients of these motions of ions and try to understand the underlying mechanism, why they can move together. And the other things is we want to understand the contributions of the third ions or the second chloride, whether or how it can regulate the behavior of these ion pairs. So basically, we just do two kind of simulations with and without the second chloride ions. And as you can see, with the existence of these chloride ions, both 3 ions can stably absorb on the site. While if we remove this chloride, these 2 ions will remove or depart from their original binding site. And very interesting, we can see they depart almost simultaneously, and their correlation coefficients is around 0.93. It's very high, very highly correlated motion. So the binding stability can be regulated by these chloride ions, and these 2 by the second chloride ions. And these ion pairs did realize a very stable transportations. And then we try to understand how they can realize such highly coupled motion. As we can see, if the ion want to bind very stable with proteins, apparently they should have strong interactions with residue. And that kind of stable interactions may disrupt the couplings between these 2 ions. So it's kind of paradox. And we try to understand why they can still realize both the stable associations and the coupled motions. The mechanism is like this way. The binding mode of potassiums and chloride are very different. The potassium, they can spontaneously bind to 2 pairs, 1, 2, 3, 4, 2 pairs of residues, and arrange in a very stable tetrahedron configuration. It's very stable and very well defined. binding pocket. And the binding energy is also very high. It's like minus 190 kilojoule per mole. It's very stable way. On the other hand, the nearby chloride ions just bind to two kinds of radials, and their interactions is very modest. It's like minus 20 kilojoule per mole. And it's much smaller than the interactions with potassium, which is minus 123 kilojoule per mole. So, in other words, the binding stability of chloride is largely attributed to the interaction with potassiums rather than the residues. So so there's only one, the last pieces puzzles we left. If the potassium ions move firstly, and you can always drag the chloride with it. So the last pieces is whether the of puzzle is whether the potassium will move firstly. So that is related to the contributions of the third ions. The third ions or the second chloride is just incubated into a loop and cause deformations of this loop. And the removal of these ions can cause the structural realizations of the whole helix and drag the two residues of this tetrahedron binding pocket away from its original state. So that disrupts the whole tetrahedron binding pocket and cause the departure of potassium. And the potassium will drag the chloride with it. So that results in the dissociation of whole ion pairs. So the Science magazine quote our studies is based on the structure, functional studies, and the molecular mechanism, molecular dynamics simulations. We propose an ion transporter model. So that is basically I want to show you, and I want to thank my students. 新闻 is in 香港科大，张卫新、韩明明、徐中和 and our collaborator Sri. We have very intense discussion with Sri, and we want to thank experimental collaborators. Xue is his first author of this experimental collaborator studies, and Cao Yi, Wang Wei, and the MMR guys, Yang Lingyun. And thank you for your attention.